And as everyone is going ahead and downloading and installing everything, a quick reminder that if you did already download the zip or pull the repository, you should do so again because we did make changes this morning. But yeah, so as a brief overview of what we're going over, we have about 4 sections, and each one will be about 45 minutes long with a 15-minute break in between. The first one's just going to be going over basic NumPy arrays and how like a NumPy array is an image. And then we'll be like looking over some filtering algorithms in the second part. And using napari for some interactive image segmentation in the third part, and then doing some more advanced exercises in the fourth part.
Yeah, so the fourth part's actually totally new and experimental, but it'll just depend on what people are watching. Like, yeah, it's basically a free thing. So if you have data that you're interested in analyzing, free to here. We can also sort of walk around and use your data.
Okay, so I'll get started on the first part.
Wait for a few more minutes.
Okay.
Yeah, if you're done installing and you've got a Jupyter, can you show the homepage?
Which oh, this?
Yeah.
Okay.
If you're at this page, then put a blue stick.
Yeah, we want to have this open. Just click tutorial and open your stuff. Okay, so fundamentally, images, they're just arrays because, you know, they're like a collection of data, a matrix of data, if you want to say, and that can be represented in this sense. So first, we want to show you how you can create a grayscale image, and it's just going to be a 500 by 500 pixel image over here, there. I don't know why it got cut off. Very interesting. Let me just rerun this. Okay, yeah, I don't know why it just didn't render it properly, probably because it wasn't fully on screen or something. But anyways, hopefully for you it does work properly and doesn't just show half of the image. You should see a full square image here with a bunch of kind of static and a bar showing you the values. So it ranges here, you can see from white is set to about 1.0, and black should be all the way at the bottom of this color bar being 1.0. And just to show that we can do this with, you know, actual images and not just like random junk we just created, we're going to pull up one of our favorite examples from the scikit-image data set, example data set, I should say. That's going to be coins. So this better show the whole thing, I swear. Anyways, why is it freezing?
So the kernel's clear, so just run it again.
Oh, yeah.
Wow.
Issues. Guess I restart the kernel again.
I'll give it a go, but I think I like Lars's suggestion to try to survive. Anyone else having issues?
Great. It's just me.
You're perfect.
Just the presentator. Yeah, yep, okay. Oh,
Yes.
yes, there we go. Okay. Third time is the charm, it seems. Amazing. But yeah, here we're just printing out the type of the image, or like, I guess what we're representing it in, which is, of course, NumPy array, and the data type, which is an unsigned integer, and the shape, which is, just, how many pixels. It's like what you would classically see. So it's a bit different, because normally when you see like image, you say, oh, it's width times height, but this is actually height times width, as you see here, because this goes along to 300-ish here and past 350 here. And that's just because inside a matrix, it's represented as rows and columns, and yeah, that's just how it works out visually. So this is where we start to get into some maybe like more hairy terminology. So you can have a 2D image that is a 3D array, and that's because the third dimension of this image is actually encoded as the color. And here's an example of that, using everyone's favorite cat, Chelsea. And we can go ahead and also check using the built-in NumPy methods, the minimum and maximum values. So, given this, and how, that third dimension that we're talking about is just the RGB values, red, green, blue, we can go ahead and create a red square by simply using this former picture we had and taking some indices of it and setting them so that we have red at its maximum value, and so we'll just impose a square over the cat, as you can see here. And just as a side note, sometimes it can include a fourth channel, so instead of just red, green, blue, it can be red, green, blue, and alpha, and that alpha just tells us the transparency or opacity of an image. So here's like a little cheat sheet on like what we mean, what kind of array we're talking about when we say a certain image. So a 2D grayscale image is just, there's only 2 dimensions in the array. It's just the row and the column, and that just corresponds to a value that tells us like what intensity it is along black to white. And then multi-channel is a 3D array with the row, column, and the channel being RGB or RGBA. And then 3D grayscale is, again, just a 3-dimensional array, and similarly, once you add in color, it becomes 4-dimensional. So we're going to head and display some images with matplotlib. So we're going to, again, use one of scikit-image's example data sets, so just go ahead and load that in. And here you don't need to know all the fancy matplotlib stuff, but essentially we're just gonna create a side-by-side of our cat and a rocket. There you go, isn't that cool? So if you're interested in like doing fancy stuff, like for example, you can turn off like the axis labels, or you can add more, or you can even add like a little legend. Simply just check out the matplotlib documentation that is linked inside the tutorial. So, we were talking about grayscale images before, and like a certain value is black and a certain value is white. So typically they're represented in two different ways. There's it going from 0 to 1, where 0 is black and 1 is white, and this is just a floating point value. I think that one's pretty intuitive. The other one is 0 to 255. 255 is because that's like the maximum value for an unsigned integer of 8 bits. And so when we don't know like what we're dealing with, we can simply use a utility function from scikit-image. And I guess this is just like a little example to show that like these are literally the same thing. But we can go ahead and convert something to a float or as a U by using utility functions from scikit-image. And here you can see like an example, like you might get passed over an array and you would just automatically convert it to a float image before going ahead with your calculations. That way you don't have to do like any fancy extra logic. So, image I/O. In scikit-image, there's a few different ways to import images. The simplest is just using the IO's imread function, and this loads something from your local file system. So here we just loaded a picture of a balloon. So nice, so colorful. But you also have the ability to go ahead and like query for like a bunch of different files. So here we're searching for anything that has a PNG or a JPEG suffix within the data directory. And we have two different things here, and we're just going to plot them again. Wow, isn't that cool? Just like as a random aside again, we used enumerate here. You may or may not have seen this before. Enumerate basically gives us the index of the thing we're iterating over, or the item from the thing we're iterating over as we go through it. So here we have like animals, cat, dog, leopard for some reason. I don't think anyone would want a leopard as a pet, but who knows? So here, enumerate, it gives us the index here, I, which is 0, because remember, everything in Python is 0 indexed. And yeah, the actual item that we want as well. So now we're going to get onto the first exercise, and this is going to be drawing the letter H. So kind of similarly to, if you scroll up to when we made that red square, you want to do something a bit more advanced. You want to be given an image and any coordinates. You want to be able to take that and just draw an H on it. So the H should have a total width of 20 pixels, a total height of 24 pixels, and then each like little, arm or segment of it should have a thickness of 3 pixels. So we're going to go ahead and give you, 8 minutes to do that. Okay, yeah, it'll be adjusted to sticky notes, but wow. I could also pull up like a video for you. Maybe that's more exciting. But yeah, please show us with your, please take down your previous sticky notes, or put up the ones according to your current status. Okay. Just like as an aside, the reason why we do image.copy here is because since you'll be modifying the image in place, we don't want to modify the original image. Sure. Okay, yeah, I guess if you finish this exercise early, you can also go on to exercise 2, and you're just going to visualize that RGB channel. Remember that it is the, if we go back to our little cheat sheet up here, you can see how these images are typically encoded. So the channel over here is typically the last dimension of the image. So we want you to go ahead and slice it so that we can isolate those channels in exercise number 2. And additionally, if you're like interested in color theory, you can take a little jab at, here it'll show you 3 different circles. One is red, one is green, one is blue, and try to think in your head, what is this going to look like when you combine all 3 together? Remember that when colors overlap, they can create different colors, so. But anyways, yeah, so there's 2 different ways to do it. First way I'll show you will be a bit like more crude in the sense that I'll be kind of like hard coding a lot of stuff. And the second way I'll be using something like a bit more modular and cleaner with variables. And you could kind of get a sense of how you might be able to add those variables as additional parameters to your function, for example. But first things first, I want to extract the row and the column out of the coordinates. So I'm just going to do that for my own sanity, so I don't have to keep doing like chords 0 or chords 1 over and over again. And so we're starting from the top left corner of the H. So that means that in our array, we're going to be starting from, remember that row is kind of like that y-axis, and column is that x-axis in this case. So we want to basically draw like a subset. We want to draw 3 different rectangles to like represent the 3 parts of that H. So I'm going to draw the first arm on the left side. And since, we're starting from these coordinates, first of all, we're going to start from here. Then, because this is supposed to be 24 pixels high, we're going to add 24 here to the end. So this is taking a range of values, so starting from the starting point and then adding all the way 24 down. And here for the column, because we have a width of 3 pixels, we'll do a similar thing. But instead of 24, it's going to be 3. And we're just going to assign the color to that. And now for this second one, it's going to be, actually I can even just copy paste this, it's going to be really similar. But the difference is it's going to be shifted, the other arm of it is going to be over more to the right-hand side. So that means we're going to have to add something more to the column. And so you might think, oh, you'll just add 20 in this case. But remember that because the total width is 20 pixels, and we do have like a thickness of 3 pixels, we'll need to do some, basic arithmetic. In this case, I'm just going to hard code 17, which is that the total width minus 3, which is the thickness, or I can just even just write it here. And then lastly, we're going to create that center strut. So, the strut is going to be in between the bottom and the top of the arms. So we want to get the middle of the drawing basically, and that's going to be 12 because 24 divided by 2 is simply 12. So we're going to start with row plus 12, and then the column is simply going to go column to column plus 20, and this will overlap with some of the other stuff we did, but that's fine. And then to account for the thickness here, it's going to be a little bit more tricky. So because the total thickness is 3, that means, so right now if we were to just run it like this, you would have a very thin center strut that would just be 1 pixel thick, and we want that to be 3, so we need to add 2 additional pixels or lines of pixels for that strut. So we do that by first subtracting 1 from this 12, which is the midpoint of the vertical height. And the second part is we're going to add 1 higher, but an additional caveat, we need to add 1 even higher onto here because due to the indexing within Python, for example, if I were to type in here, it's let's say I type in here out 0 to 3, it'll actually only iterate over 0, 1, and 2. And that's why we're adding the extra 1 over here. So hopefully I didn't mess up and be super embarrassed. This should just work. Amazing, it does. So now I'll get into the second way of doing it. And Juan told me about this last night, and I thought it was pretty cool. It's a different way of thinking about things, so I thought, why not? So there's actually another method of doing this. And actually, first of all, for my own sanity's sake, I'm going to actually assign the stuff we have to variables. So, we have the height of 24, width of 20, thickness of 3. And as I said, you could even take these and plug them into the function and change the function signature. And that's how you would, for example, modify it. Anyways, so basically what someone did was instead of just drawing the H over it, what they did is you can get a subset of the array in NumPy. So they got essentially the bounding box for this H, and they separated it, and that made a lot of the logic easier. So how we would do this is we would get the subarray would be out row to row plus height column to column plus width. And so we've gotten our subarray there. And now, let me just delete these actually. So now we can go ahead and create these arms and strut again. So it's pretty simple. For the first one, all you need to do is get that height. So when you just start it off with the colon and nothing beforehand, that's implied that it starts from 0. And similarly, if you put it at the end, like this, it means it starts with the index of height and then goes to the end of the array in that path. Okay. So if we can see here, so we have this, and then we do column to column plus 3. But because we've already taken the subarray, we can forget about the column part. So actually, we can just say thickness here. Okay, and now we'll simply repeat that for the other part. So let's assign an intermediate variable to capture like the index for where the second arm should start. So arm index equals width minus thickness. And again, this is because due to the thickness of it, we don't want it like, you don't? Minus index. Wait, what? Oh, that works. Amazing. Today I learned. So basically, for context, when you put a minus in front of it in the first part of the range here, that's just telling it like -1 would be get me the last or second to last element from the array. So that's just what we're doing here. And then we want to get like the midpoint value, right? So we're going to take the height and we're going to divide by 2. The reason I use 2 slashes here is because that ensures it's an integer. If it's a float value, which it will be if you just use 1 slash, NumPy will complain bitterly. So. And here, you can just even just leave it as 1 : because it's just going to be literally everything in that value range since it's the bounding box already for the column. And then let's go ahead and apply the thickness. So because we're, again, taking the middle of that, and we want to basically add like however many pixels we need to on each side of the strut, we're going to get the thickness and divide it by 2 as well. And so from here we'll have this 2, and then that +1 at the end, of course. And here we can, you know what? Oh. Let's see, it's because I forgot to assign the color. There you go. Less embarrassing now. Okay. So now we'll get on to exercise 2. And this one, I think, personally, I think it's considerably easier. So we're going on to, we want to basically isolate each channel here. And as we said before, since this is like a 2D color image, it's going to have the format of row, then column, and that channel. So that basically we just want to isolate that last channel. So you can do that. So here we just, that's the row, that's the column, and now this is the channel. And the cool thing with NumPy is you can also abbreviate this by simply putting an ellipsis, and that's basically just saying like fill in all of the dimensions here and just get like me the very last one. Here it should just work. Awesome. Okay, so
What's the NumPy golf version of this? We do all one I would do
there's
R, G, B equals empty dot net
So now here already ran this, so like we wanted to see like get your imagination running, like what would it look like if this is red, green, blue? What would the composite picture look like? So we can actually compute it similarly to here. So if you noticed here, to get the like composite picture, or the one with all of the channels together, you just had to stack them. So we're going to simply plot.mshow, and these were labeled red, green, and blue, so let me change these, and it should just work. Awesome. So you probably have seen this symbol somewhere on like, I don't know, MS Paint or something. But now you know how to create it for yourself. Right, sorry. Yeah, so it's plot.mshow, numpy.stack, and then you just stack together red, green, and blue along the second axis. Axis 2 because, remember, it's row, column, channel, so 0, 1, 2. And then lastly, hopefully you've had some time to be able to do the third exercise. So here we're given some coefficients, and we want to basically do our own method of like converting to grayscale using these coefficients. And of course, like all of these sum to 1. So here, we can assign our coefficients as an array. You could do like numpy.array like around this, but I'm just going to use a list because I'm lazy, and NumPy will do the magic for me. Simply because the other array is a NumPy array. Okay, and you would simply just use matrix multiplication with the coefficients. There you go. It has a pretty similar result. They also had like a little mini exercise inside, like if you just changed it to 1/3, so you can just change these to, 1/3 each and run it again and see what you get. Does anyone have any questions?
I'm going to talk about the second part. First of all, my name is Lars. I'm also a scikit-image commentator, and we are increasing the. We're not increasing the difficulty, but we are talking about a bit more advanced image filtering stuff. And basically, what is image filtering, or filtering in general? It's the process of removing some part of a signal which we don't want. That can be basically anything, but you can talk about filtering in a lot of ways, and we'll start focusing on local filtering. So the local keyword should already give you a hint. It's about looking at a part of the signal, looking at the surrounding parts, and adjusting the signal based on that context. So you don't look at the full signal, you just look at an excerpt. And for that, we last section we focus on images, but for this first part we will just focus on very simple images, which are one-dimensional, still images, one could call them. And we first generate a very simple signal, which is just a step function, which goes has 100 samples, and at the 50th samples we just have a jump at the top end. Let's say this is the original signal we want. And now we simulate that we have some process which is adding noise to that and making our signal very hard to recognize. I mean, you can still sort of see the original step function, but it's not very easy to extract or maybe work with if you want to do some automatization in there or detection. Let's say, for example, you wanted to have the average niveau of the step, like what's the average high plateau of this, it wouldn't be very easy to compute. So what can we do? We know that the noise is changing a lot, very fast, between samples, while our original signal is changing very slow. It basically only has one change. So we could try maybe average a bit. We can do so by just adding together neighboring samples. We can do so easily with NumPy slicing. We just here we just take the signal and slice off the last pixel or sample, and here we start from the first sample and divide by 2 to preserve the original values of the signal. And if we run that, it's already gotten a bit better. So we still have some noise, a lot of noise in there, but it's smoothed a bit. And let's see what happens if we do this again. If we take another pixel, so now we are looking on both sides or of one pixel. And here we have a plot where you can more easily see the smoothing effect. What you also notice maybe already is that the signal we are filtering is getting shorter and shorter. We'll come to that in a bit, but it is something you have to keep in mind. So we could, let's say we wanted to smooth it even more, we could repeat this process and add even more stuff like this, but that can get kind of tedious, and I don't really feel like doing it that way. So what we can do instead is we can specify this averaging as a kernel. A kernel is something like basically a small pattern which we apply on each, which we move over the image and it's basically a set of weights you move over the image, and you add together the weights times the pixels at the current position, and you get a signal. And this is called convolution. We can see it in action, so maybe that it gets more intuitive. First, let's talk about the kernel maybe we are using. It's, let me just quickly print it. So an average kernel for the example we have above is basically we add ones instead of the signal itself here, but we still gotta divide by 3 because we want to preserve the energy level. And we do precisely that. If we look at the kernel, we have each weight is contributing 1/3 to the signal, and if you apply this over the signal, you get the smooth signal. We can see so in action more intuitively with this interactive plot, which is, I think, a very nice way to visualize the smoothing. So we see the blue samples, which are where the current kernel is at, and the orange one is the resulting value. Like if you add each of the blue dots, you multiply by 1/3 and add them together, you get the orange one. And you can move this along over the full signal. Yeah. Okay, that too. We can also do so, and I think that's good. We can do a lot more exciting stuff. We can use this for a longer kernel. In this case, 11 samples wide. So we divide by 11 again to preserve the that the kernel is still on average, or is the total sum of the kernel is still 1. And if we do this, smoothing with it, it's getting, I'd say we start already recognize the original shape of the function in a lot nicer way. And it's also cool to look at this with the interactive part. You can play around with it. So it's starting to climb up now when we get to the high rise of the signal. And here we are running into the edge, so we don't have a lot more values to compute. So let's talk about that. We've seen that when we do this kind of filtering, we are also shortening our signal, but that's something we may not want. And we can NumPy provides a way to deal with this. We can just if we don't specify anything, convolve is using the mode valid, which means it only shows samples which where the convolution between the kernel and the original signal. But and this is why it's getting shorter, because for valid, to get a valid result, you can't, you have to have an overlap between both kernels. So the kernel size is shortening the output you get. But you can, NumPy supports the mode same, and in that case, it just pads the signal. We could have done this manually by just calling NumPy pad at zeros, and then it just applies the mode valid again. And what we see now is, because we are padding with zeros, it's starting to drop off, because at this point the kernel is seeing zeros on this side, so the signal goes down. This is an edge effect, and that's something we have to think about if we do filtering. May not be important at all, but maybe something we want to do something about. So you can see this in action as well. You see on the left side there's also zero padding, but this doesn't affect our signal, because in this case we don't have a lot of deviation from the mean zero. But here you see the padding with zeros. So now we come to our first exercise. There's something we can do about it, and that's something which is SciPy is providing. So the first task is to look up this function, maybe read through the parameters, hint, look at the mode parameter, and see if you can filter this image without having this drop off at the end, this edge effect. So obviously we have to import SciPy to use it. Note that I am using it this way, but I could also do it this way. But SciPy, I think it's quite nice that SciPy now supports this. Basically, you only need to import the top level, then you can just use it like shown there. So we use the same kernel, obviously, which was called in kernel 11, the 11 sample-wide one. And if we go into the documentation, we see that there are several modes, which are, for example, called mirror or reflect. And what they do is they take the part where the signal ends and just reflect it or mirror it on the same.
Lars, do you want to show the docs?
I can show the docs here. Let's make it smart.
Do you have a shortcut for switching to SciPy?
You don't?
No.
Yeah. I don't have time. Yeah, there are several modes in here which you can use for different things. For example, basically we are if we don't specify anything, like with the NumPy solution we were basically implicitly using the mode constant with a 0, which just means we add, once we get to the edge, we just add the value, which is in this case C value, as long as it takes. But we could also, for example, use wrap, which can be an interesting mode where you just start the signal again and start repeating it. That can be very interesting if you do some frequency analysis. But or you could, for example, use nearest, which is just taking the last pixel it finds and just extends it toward the left. But for example, we could also use reflect, which is just emulating like the signal going on, and especially if it's not that long, it can be like can work. Just know that what you're doing here is you're in some way or another you're creating signal that doesn't exist. So don't put too much stock in what the result you're getting, in the sense that it's not a true signal, it's something you manipulate. So that can be totally like expected. It's just a way of going about data that's missing, And if you have nones, you also have to think about how you replace them. So let's use the mode reflect here. And already find a variable here and run it. And what we see is, because I overlaid it with the signal where we don't deal with the edges, you can see very nicely that the difference in this area here. It's not so big here because, like we talked about, the basic mean of the noise here is also 0. Oh, it's was showing me 2 plots. Okay. Yeah. So we are still let's get to the next section. This is still local filtering, but instead of smoothing, let's say we are not interested in the slow change of a signal, but especially the part of a signal that's changing fast. Or for example, if you have an edge, in our case, you remember that we have this step function. Maybe we are interested in where does the signal change a lot. And if we want to answer that question, we can also do some filtering, which is basically we are trying to remove slow changing parts of the signal. And here we have an exercise which we don't have to code. It's just I want to give you a moment to reflect on this. We have basically NumPy offers 2 functions which are kind of doing the same, but because I will get to that in a minute. Convolve and correlate are applying the kernel in a different way. One of them is applies the kernel inverted, which is for I don't want to say historical reason, but because of it's a convention in signal processing. And if we look at this, we see that. So let's talk about this kernel. This kernel is, instead of having equal weights, it's weighting different parts of the signal differently. If you imagine we are at some point in the signal and we're in the flat part of the signal, we have -1, 0, and -1. All times 0, it's 0. So we get what we expect here. Here we still get 0 because -1 times 1 plus 1 times 1 is still 0, and the 0 in the middle isn't contributing much. But here it gets interesting because then one part is on this side, the 0 is maybe somewhere here. We see that it's actually, I think, 2 samples wide, and on the other side of the kernel is already here. So in that case, the 0 and the -1 and the 1 start to constructively add up, and we get either a positive result or a negative one. And that depends on how the kernel is oriented. For example, if we have a -1 is here and the 1 is here, we are expecting a positive one. And if it's the other way around, -1 times 1, it's orange. So we see that the convolution is actually inverted because the -1 is the one is on the right side of the kernel. So for the rest of this tutorial, we are, for ease of understanding, we're going to use correlate, which is just representing and applying the kernel like we are actually defining it. So in case you're using convolve and are confused, for kernels which are symmetric, that doesn't make much of a difference, obviously, but if you have a directional one, you might get a different result. Of course, if you only care about the value and not really the sign, then it doesn't really matter as much, and you can just take the absolute value. What's also cool about these kind of filters is that they are we can apply them one after another to an image. But first, let's apply the kernel we are having to our noisy signal. And what we see here, or maybe I think you can kind of see it, the basic step in the background has been removed. So the baseline of the noisy part on the right side is, I'd say, also around 0. And but this is still very hard to see. So if we said we are interested in this step, and we basically want to find the obvious part of the signal where it changes, it's very hard of noise for if we have noise in there. And that's, I think, very characteristic for these kind of filters, that if they are very, sensitive to noise being in there. And what we can do about this is do both. We can smooth and we can try to changes. And in that case, it's a bit about finding the right balance between the two. Like if you smooth too much, then you also remove the noise altogether. If you don't smooth enough, you might get a result that still looks a lot like this. So filtering is, like many image processing methods, also something you kind of have to play around with. And I think a good paradigm to follow is always look at the signal, at the data you're getting, and get a feel for it to see what kind of filters or values can work. And yeah, in this case, what are we doing? We take the smooth signal from earlier. You remember the ones where we did smoothing with 3 by averaging over 3 neighboring samples. We correlate it with our edge or our change detection kernel. And here I've overlaid all 3 signals, like the noisy signal, the change we detected earlier where you couldn't really see much. I mean, you have this huge peak, but it's not maybe not as different from the other ones. And here we've added smoothing as well. And I'd say we're starting to, if we tune it a bit, we can already see, okay, maybe around here there's some huge change in the baseline, and we're actually seeing that. And I said earlier that we can apply these filters one after another, but we can also combine them in a single step. Basically, they are commutative and associative. You can just, instead of applying them one after another, you can just combine the filters before and then apply them on the signal already. And here we do that. We correlate using mode full, because we don't, if we use this kernel, we actually want to, it's getting wider. So what was before 3 samples wide is now 5 samples wide. This is because of the overlapping, I think. And if we apply this, we get nearly the same result. The reason for the slight shift in here is because the smooth signal from earlier, I think we did that with by removing a pixel at the edge. So you're actually seeing here one of the signals being shorter. And yeah, I think in this case it's nice, you can see both signals more clearly. So up until now we've used some very simple mean filters, like basically just all weighted the same. And we've looked at a case where we weighted asymmetrically, but still with the same weights. What happens if we use different weights? And in image processing, a very common kernel is the Gaussian filter kernel, which is, I don't want to go too deeply into this, but the Gaussian kernel is a very interesting filter, because if you look at it in the frequency response, it's actually having some very nice properties which are keeping the image, which is not introducing in a lot of noise due to the filtering into the signal. We will see an example later where we can more clearly see this effect. But for now, let's look at this Gaussian kernel. So the Gaussian kernel is, we're not having a lot of samples here, so it's not looking very smooth, but it's already having the Gaussian-like shape. And note that we can also convolve it with an edge detection filter, in which case we get this interesting looking function. And it's basically got the smoothing properties of a Gaussian kernel and the edge detection properties of an edge detection kernel. And if we apply this, I think you can already see that it's able to deal with the data a lot nicer. I think this peak in the middle is standing out a lot clearer as compared to here, where we still might consider this some actual change instead of the noise. So up until now, we've not really applied this to images, but let's do that now. First, I'm going to define a very simple signal just to have some simple cases where we can see how this works. And let me plot it. So we're defining an image which is, I think, 7 by 7. And in the middle we have a white square, which, if you remember our last part, is just represented by a white. Like if we were to add a color bar here, the higher valued pixel get assigned white, or a whiter color, and the lower value ones a darker color. And in this case we only have 2, so it's white and black. But we're gonna see in a minute if we have some values between 1 and 0. And let's define a mean kernel again. This time we are having to take into account that we have another dimension. And how can we deal with this? We just add another dimension, and we, instead of dividing by 1/3, we divide by 9, so that the kernel still has a sum of 1. We can look at the kernel, nothing surprising, I'd say. And yeah, let's run it on the image. So you can kind of already get a sense how this might look. I think it's looking nicer in a minute. But what you can actually see is the square in the middle has gotten wider. So you can talk about this like values which are close to bright values are getting brighter, and values which are close to very dark areas are getting less bright. So it's kind of muddying it up a bit, except for the one in the middle, because at that position the kernel is just, remember it was 3 by 3, so in the middle it's just covering the entire bright area, so we still get a 1 here. And now let's have to look at a very nice demo here, where we can see this filter in action. So the first, there's nothing happening much because we are just having zeros here, but here we're starting to get some values, and we can see that the more the kernel is covering the bright part of the image, the brighter or the higher the resulting value gets. And we're assigning the value, basically the sum of this kernel, the weighted kernel, at the position we are currently at. So that's what I mean by we are moving a kernel over the signal. It doesn't really matter in which direction we're moving, because we're always mapping the position to the current pixel in the output. And also remember, here in this case we are not seeing really, or we would be seeing edge effects, but we don't, because it's just zeros, so it's not impacting the signal. But if we, for example, consider that the outside of this image had the value 1, we wouldn't be getting a black edge, we would be getting an increase in value again. So this is the final result. So now let's apply this to a real image. For now, we're taking the camera image from the scikit-image datasets. We are taking every 10th pixel so that we can see the filtering a bit more in detail. We will look at applying it to the full image later on as well, but if we take every 10th pixels, obviously we get a lot pixelated image. And let's try to, and also this kind of, yeah, that's all I wanted to say in that. And because we will be showing images besides each other, this kind of presentation is very useful. So let's quickly define a function which just displays images side by side if we give it to them. and adding the title. And now we can apply the mean kernel. Remember the 3x3 kernel we had to the pixelated version of this camera image, and give it to this function, basically pixelate, filter it, and the appropriate titles. We see the result. What I do want to point out already is that you maybe pay attention to this kind of area. This will get interesting later on, where you can see difference between mean filtering and Gaussian kernel filtering. And yeah, that's what I'm coming to now. So I already hinted at that the Gaussian kernel is very ubiquitous in image processing, and that's for a reason. But first, let's look at the Gaussian kernel if we have it displayed, or if we use it as an image. If we apply the Gaussian filter to the mean filter, we still see we have a lot of brighter value here. But if we apply the Gaussian filter to the original square image, which we generated earlier, we see that the middle part is actually a bit darker now. That's because the Gaussian filter is actually, like, the Gauss function is never, in theory, never going to 0. It's just approximating it. So usually you could consider it as being indefinitely wide, but I think in praxis you cut it off at some point. I think it's around, if sigma is defining the width of the Gaussian function, you could, for example, cut it off at 4 sigma, or 4 times sigma. And that's why still part of this is contributing to the result here. And what's interesting is if we apply this to this signal, I said you should pay attention to this part. You don't think it as clearly now still, but basically one of the properties of the Gaussian filter is that it's less prone to artifacts when filtering. And that's because if we look at the Gaussian filter, it's actually taking in the distance of pixels in the Euclidean distance. So if you remember, if you step to the left or to the right, you have basically you have a distance of 1 pixel step. But if you step diagonally, if you consider the Euclidean distance, it's a bit wider. So if you apply just a simple averaging filter, which looks like this, then you actually, I'd say, overweighting diagonal elements, and the Gaussian filter avoids this. And that can, I think, yeah, you can see this effect here now in much more detail. This is the result with mean, and I'd say you can see some artifacts here where you see kind of weird lines which you don't see in the Gaussian sense. It's this one, the Gaussian result looks a lot more natural and smooth, like you were seeing it through maybe some rough glass. Yeah, and just to have a look at the filter I hinted at earlier, if we actually want to see how the Gaussian function looks, we can just apply it to a single pixel in the image, just basically a pixel, and then we can reverse engineer how the filter looks. Just note, if you're asking yourself why, oh no, we're not doing it. Yeah, why we are doing this. This is so that the brightness is on average again 1. And I think in this case we could, for example, cut off here. If we had an interactive plot, we could still see that it's not 0 in this area, but it would be approximating 0. So now we come to another exercise. Basically, I want you to remember earlier when we did some slicing on arrays, I'd like you to plot this slice of the image as a line plot. I'll give you a few minutes for that. think I'm going to slowly go through the solution now. So we basically want to get the line in the middle. One way we could do that is just look at the shape of the kernel and then choose a sample which is approximately in the middle, for example 21, 22. But let's be a bit more ambitious and say we don't really know and we want to write something that doesn't actually care about the size of the kernel. In this case, we know it's rectangular, but we could also just have something which is not same sized on each dimension. And if we, one way we can get something very close to the middle of the shape is always just using this kind of expression. That's, I think, it's called whole integer division. Basically, it does a division but drops the rest, which is, in the sense, it's kind of an opposite of modulo, the modulo operator. And just for the sake of doing the right thing here, I'm going to treat this example as if the shape might be different. So I'm computing the, oh no, actually we don't have to do that because we are only taking a single slice. But let's say I wanted to do the slice in this direction or in that direction, then I could do this on the second part of the shape as well. But let's do it. We actually want to do it on the x-axis, so in this case that's the col. That's the second part of an image, which is the convention. So let's do it this way. So this bit just specifies we take everything from the whole part, and just giving in a single value here will just give us a slice, a single array. So if we plot this, let's not just put it directly in our plots. So let's plot the first part, and we basically see a Gaussian curve like we expected. And Juan suggested that we look also at neighboring slices to maybe get a sense of how it's progressing. And we can do so by simply adding a 1 here. Oh, maybe we shouldn't do that. Do this outside the indexing. And we see that it's starting to decrease as we go along, and the second part of this, the Gaussian curve, is decreasing. So this has been the Gaussian kernel. Remember, in the past on the one-dimensional signal we also did some detection of changes. And in image processing context, we call this edge detection, because edges are parts in the image where there's a lot of change in values. Basically, you don't have slow changes over the image. There's not a smooth ascent of value. It's a very hard edge. And those are, in a lot of cases, very interesting parts of an image, which we want to maybe detect. So we'd ask our question, okay, we want the output of which part of a pixel in an image is involved or close to a lot of changing signal. And here we have to think about a bit that when we apply the edge detection kernel, remember we had the Gaussian kernel, which we defined as a 3x3 sample, for example, or three-dimensional one. But for now, let's only consider one direction and create a vertical kernel that we apply on the image. This means we will apply it on every pixel as well, but we will only look at the top and bottom neighbor of a pixel. That's something which you can do with kernels. You can just zero parts of them out. So, for example, we could do something like this and add zeros on each side, that would have no effect. But this is basically, if we leave this out, that's basically what's happening. And if we apply this filter here, we see we get actually to see how this outputs is basically stuff where there's not a lot of changes, in this case gray, which is, if we were to plot a color bar here, we'd have a 0 around here hovering with gray. You would put a color. Was it like this? No, that's not working. Hmm? Fig, yeah, maybe. No, I think I have to give it an. Ha. Okay. Yeah. And now you see around here where there's gray, we have something where the kernel is telling us, okay, here's not a lot of change. But where this is different, where we get a lot of change here and at this direction. And in some cases, we might actually care about in which direction we get the change. Maybe we are only interested in S-sense, where the signal is increasing a lot. But in case you ever are only interested in the value itself, you can always just do it like this. And then you basically, it's another way of putting it. You say, I don't care about direction, I only care about where there's a lot of change. And then you get bright areas regardless of whether there's a step from background to foreground or back. And yeah, we come to another exercise now. So we've done this in the vertical direction, but let's say we are caring about we don't only want to detect the change in the vertical direction, but also in the horizontal one, and we want to combine the results. And we've given a hint here, the way how you could combine these results. It's basically by taking the L2 norm, the square root of the summed squares. And I'll give you a few minutes to come up with a solution. Seeing a few more blue stickers now, so maybe I'll go through the solution slowly now. So, like I gave already, like Juan said, I already gave the solution. But I only gave part of the solution. So, basically we can copy this stuff. So instead of giving the vertical kernel, I'm going to give the horizontal one. I do. No. So maybe let's plot it already with the without combined. So if we let's compare it. Okay, this is looking a bit weird now because the color bar is taking some space here. Don't remember right now how we could get them equally sized, But what we do see is that the direction of the kernel, remember this is the horizontal, the vertical one, and this is the horizontal one. So right here at the top of the head, there's not much going on, but where there's direction in this, change in this direction, there's a lot more happening. And if we want to combine the results from these two filters, we gave this hint. So basically you just take the result of the vertical one, square it by 2, and combine it with the result of the horizontal one, also squared by 2. And in the sense, I think of like we could already display it like this, like the square root is, I don't think, changing anything in the color distribution if we just care it, but it's good practice to scale it back down to the proper values, because if we don't do the square, we get actually different, I don't want to say combined, the value of the combined result isn't comparable to each singular input. So we do it this way. And yeah, let's plot that as well. Maybe this time without the sidebar. Yeah. And now we're seeing, what we are also seeing is, because we are combining this and we're squaring this, the sign gets lost, which is expected in, when you square it. So we are also getting a plot where we are only seeing the change and not the direction. So earlier we were talking about the Gaussian kernel being a very common kernel when we use when we do smoothing in image processing. We also have a very common kernel or approach that we use if we want to do edge detection in imaging, which is the Sobel filter. It's a very similar filter to the one we've used here. So there's not going to be a huge difference if we apply it here. But first let's get a look at it with a more simple example, how it looks. We can also see it's considering both directions. So there's a change. Remember, the change in the image is where the squares meet, and we can see that it's detecting the change in both directions. And right in the middle, there's no change detected because it's just white. And if we apply this to the pixelated version of the image, we see a very similar result, I think, to this one. It's looking a lot, I think it's looking less noisy a bit on the edges, so it's a bit more consistent, and we can look at this in more detail in a few minutes, or in a few cells. And in image processing, when we do this kind of edge detection, it's common practice because these kind of algorithms are very sensitive, like I told you before, to noise. It's also common to smooth the image a bit before we do this, and this way you get basically more, you get the edges you get are a little wider, but also I'd say a lot clearer, especially in this area. You can actually get some some sense of like where an edge might be flowing, and not just something that looks a lot like noise. And one of the cool things about this is actually, if you've heard of neural networks, I'm sure you have. This is basically happening when you hear people talking about convolutional neural networks. You remember the convolution in that regard. It's basically you take a kernel, you have some random assigned weights, or you basically you try to determine which weights would be optimal to achieve a result you want to get. So you can put anything on this. Let's say this is training data we have, and this is some result we want to get. Then we can define anything here, and we can do some model fitting and try to come up with a kernel that, if we apply this kernel to the input data, comes up with the result or as close as we can get. And that's a very simple network. Let's apply this to the full-scale image here. And I'm going to do this with live coding now. We're not going to do the exercise, I think, first to speed things up a bit. And yeah, in this case, this is our original data, the input we consider, and this is the target we want to fit to. And what we can use here is.
Can you show what the pseudo weights actually are? I think there's a link to it.
There's a link.
With the pseudo. Yeah.
Ah, yeah. Here you see the Sobel weights. This is for one direction. And for example, if you apply to two direction, you have to combine this kernel. And remember earlier, these filters are associative, so you can actually combine them together, and then you get a result. Do we have that in here as well?
Circle's actually non-linear.
Okay. Oh, you can't. Ah, yeah, because yeah. Forget that I said that. So what we can do here is first we have to kind of get. We want to use the linear logistic regression model from scikit-learn, and this model expects, if we define this model. Its fit method expects input and the target weights, I'd say. So we somehow have to come up with this. And the thing is, this one has to be just a single 1D array. And this one has to be a single 1D array of each feature we have. In this case, we only have one feature, so it's actually also only a 1D array, but we could also have more than one input. But yeah, so how do you arrive there? Scikit-image has this very interesting or cool function, which is giving us a way to go over an image in basically in the way that a kernel does, without like creating the full image. It's just giving us a view of the image as if we would look at it kernel by kernel, step by step. And this can be very useful, but you also have to be a bit careful if you use it, because if you somehow, for example, were to add 1 to the result from to this, what the function returns, then you suddenly, NumPy is creating a new array for that, and especially with multi or higher dimensional data, that can blow up a lot. So if you ever use this and suddenly your memory spikes, then it's probably that. So let's windowed, let's call it windowed. So we give it the original image, which is called image. And we say in what kind of window we want to go over there. I think we could also do it this way, and it will just consider it a current, or it just explode this kind of integer in all dimensions, but I think this is more explicit right now. And if we do this and print window shape to get a sense of what the result is, we can see we have the original dimension of the image, but now we also get a 3x3 result of each view. So if we go to the 0, 0 in this dimension, we see the view of the image at this size. So the original image, if we were to plot it, is 512. This is 510. This is because if we put a window on there, this one isn't going over the edge, so it's dropping. It can't show a window of a 3x3 kernel for the edge. If we wanted to do that, we could, for example, pad it manually with NumPy again, but for the sake of this, let's not. And if we have this, we want to reshape it to a single dimension. We can do so. Window. I looked up, we printed this, so I'm just going to hard code that in. And this one is just this result. And NumPy will just reshape this accordingly. In this case, I think it's because of the data layout, it will just fit. If we print the shape of this to verify what we get, times. Oh, yeah, that's not good. Yeah, this is basically how big our training data is in this case, and here we get 9. Actually, I wasn't correct earlier when I said we only take in one feature. We actually have 9 features because our kernel is 9 pixels wide, and we don't really care where the signal is, so we can just flatten it. But as long as we are consistent, this will get us the kernel we want. And now we still have to prepare the target, Y, which we could do in a similar way. We could also try to apply as windows and then only take the pixel in the middle, because remember, if we apply the window, we do some calculations, some filtering, and then we want a result of the pixel in the target. That will be always the pixel at the center of the current window. But we actually don't have to do that. We can do this in a nicer way. We can just take the target, just slice off the edge. Then we already have our reduced input, and then we just need to reshape it to one dimension. We could also use reshape here, but we can also just use revel, which is just saying, okay, let's just put this in a 1D array. Now if we do this, I did everything right. It's actually giving us a result, and if we reshape that to 3x3, we get something which is the actual filter that's used in this case. I think this image was created with a Sobel horizontal filter, so it should look similar to the horizontal Sobel filter we looked at earlier. So we have 1 or close to 1, 2, -2, -1s, and if we do what am I missing?
Except there's a scaling missing, so they're not going to get.
Ah, okay, yeah, the scaling is apparently missing. So, but yeah, because I'm calling round and if I'm missing the scaling. Some will be 0. So I can't. Okay. It's 2 point. Or what do you mean?
45, not 5.
Okay. And yeah. Let's go around again. Yeah, this is looking a lot closer. Actually, I think this is turned around.
No.
Is it? No, because of. But that may be because of the way convolution is defined in there. Yeah.
Yeah, that'll be.
Yeah, but it's you can see it's effectively doing what we expected here. It's approximating the Sobel filter, and we just we just got that from looking at this direction without actually taking in the information we had earlier. So Juan already mentioned, for example, Gaussian filters are linear filters. But there are also nonlinear filters which just can do anything. They don't apply a kernel, but they can, for example, apply a function where you don't calculate the sum of weights or some different function. You can, for example, just take the median of the whole kernel which you're looking at. Or you could also get some other statistic like the variance or the standard deviation. And if we look at this in the sense of the pixelated image, remember earlier the Gaussian, if we take the median, the effect is that we preserve a lot of the sharp edges, which we don't do as much with the Gaussian. And in some cases that can be very useful if we want to remove some noise, but still at a later point do edge detection. And this difference is especially noticeable if we apply it to the coin data set, which you saw earlier, where we still get very nice sharp edges for this case.
A miracle. All right, so we're going to talk about segmentation. Segmentation means finding the different regions of interest of an image. And if you've ever seen Terminator, then that's what Terminator is doing in this picture. It's like segmenting out the human in a broader image. So the question is, can I hide this? Very good. Yeah, so what we're going to see is how do we represent segmentations in Python, and some ways of doing them. You probably have heard of deep learning and how good it is. So ultimately, here we're trying to show you the basics, and then if you see some of the later notebooks, deep learning is you can plug that in wherever you want, but you still want to eventually get to the same data type. So that's what we'll cover. Okay, so here's a very basic example of segmentation. It's taken from the scikit-image gallery, which I highly recommend you check out. Whenever you're trying to develop something, you can try to find something that closely matches what you're after. And in this case, we're using watershed segmentation, and I'll talk a bit about that after we look at the example. Okay, now what have we done? Oh, I called Jupyter Notebook from the wrong environment. All right. Well, you can see it's not just you with the environment issues. On the activate. Very good. Tutorial. 2. All right, hopefully this one will work. Kira, I'm getting flashbacks. Kernel starting, okay. I don't know. I feel like they changed the default at some point. Or maybe, no, maybe I have some matplotlib config deep in my thing that I've forgotten about. Yeah, that's probably it. So there is a, is this what you're talking about?
Yeah, I didn't have PLT defined anyway, so I'd add that.
What? Okay, well, sorry everyone. Let's add that in here just so everyone knows. I must have a config, but I thought I deleted that config because it was giving me other issues. I do have, like, normally I have auto import NumPy, SciPy. Yeah. It is a dangerous thing. Okay, as PLT. Sorry about that. All right, here we go. Yes, that is much weirder than just the inline config. All right, so what have we done? So we have an image which is 2 blobs, but they're sort of touching, and we want to say, all right, these are actually 2 separate blobs. So what segmentation is to define a new image where every different entity in that image has a different number. So this is now blob number 1, blob number 2, and a background of 0. And the key thing to know is that the labels are just different integers. They don't actually have any meaning in terms of intensity. But you can still display it as an intensity image, so you can see that this is, actually this is the lower value. So it's 0, 1, 2. But from a computational perspective, this is like a strictly different type of image, and all that we care about is that the labels are different between these 2 regions. Okay, so now we're going to introduce a different way to look at the images. That's not matplotlib, and that's called napari. Napari has some advantages over matplotlib when working with images specifically. One is that it's an OpenGL canvas, which is more interactive. There's layers which you can turn on and off, so you can see different parts of what you're doing at a time. And also it's n-dimensional, so you can look at 3D images, 4D images, and that's going to come in handy a bit later on. Okay, so you probably need to import napari here, huh? Shift enter. Sorry? Oh, is it? Well, that's also weird. Oh, I know what's happened. This used to be napari only, but I wanted to change the transitions because we hadn't done napari before. Okay, so this is the napari viewer. And I'm just going to give you guys a bit of time to play around with it. So there's some suggestions for things that you want to try out. Doesn't work? Oh, sorry, the initial boot, if you've never launched napari in that environment, it's doing, like, a lot of the icons and stuff are, like, generated for the first time and cached. So it'll take a while to boot up, but it should pop up eventually. If there's an error, put a red sticker on. Yeah, put some yellow stickers. When you've done all of these things, put some blue stickers up. All right, so let's have a look. So as I said, you can, as written there, you can zoom and scroll zoom with scroll and pan with click and drag. You can turn individual layers on and off by clicking on the eye icon. You can option click on the, no you can't. Sorry, that's not in this version yet. It's only on main. That was dumb. Hang on. Nope, fail. Okay, so you can also change the opacity on a layer. So let's say I've got this one. So you can see that now there's a bit of blending going on between the labels and the image underneath it. So we can change the opacity on the labels layer to change the amount of blending. If you want to see all the layers at the same time, you can turn on grid mode. Or you want to make them all visible, and then you can sort of look at them side by side instead of overlaid on top of each other. And you can also paint. So if you select each label, so there's image layers and labels layers. Labels are segmentations. And you can actually grab a label, and then you can paint with it and edit the data underneath that. So obviously, you may or may not want to do this, depending on your workflow, but it's handy if you want to tweak the results of an automated algorithm, and we'll get into that. Okay, so I'm going to close this. Now we're going to look at some 3D image data, which is a little bit different from what we've seen so far. So Cells 3D, again, comes with scikit-image. It might trigger a download for you guys. And it's got 60 slices, 2 channels, and then a 256 image by 256 per slice. It has data type UN16, and the maximum intensity value is 2 to the power of 16 minus 1, which is that. This you would have to find out from the doc string of that function. So you can do data.cells 3D question mark. And then it will tell you that the voxel scaling is this, 0.29, 0.26, 0.26. So what this means is there's, between different Z slices, there's 0.29 micrometers in this particular data set. Okay, so we're just going to save that for use later. By the way, at any point, if I'm going too fast or whatever, feel free to shout out. And now we're going to look at the viewer. And actually, I want to show switching between 2D and 3D, so I'm going to get rid of this line. Actually, I'll just comment it. Okay. So we add Cells 3D. We tell napari what the channel axis is, which is 1. So the channels are on the first, if you're doing 0 indexing axis. We specify the scale, and we specify the names of the 2 different channels that we have. So if we do this, we get a viewer. Now this is something that matplotlib can't do, which is that because it's a 3D image, we get a little slider here, so you can look at all of the different Z slices. Everything else is the same. And you can also switch from between looking at 2 dimensions and looking at 3 dimensions using this button here. Okay, so this is the toggle number of displayed. So you can see now we're looking at 3D, so the slider goes away, and you can rotate the images and stuff. Okay, this is actually only for saving the book. We're not even going to do it, but you can see you can set the angles from the command line. So I'm just going to give that a go, actually. And you can see setting the angles in the Python IPython window will set them on the viewer simultaneously. Okay, so we've already seen subbill filters in the previous lesson. Like to have a thread going. And we also saw that subbill weights were sort of hand designed, and you could alternatively learn them, or you can look at different hand design weights. So the char filter has slightly different weights of 3, 10, 3 instead of 1, 2, 1 in the smoothing direction. And there's a Farid and Simoncelli filter, which is even more advanced. It's actually a 5x5 filter. And all 3 will work for n-dimensional images in scikit-image. We're just grabbing the membranes. We're just using floating point values because it's easier. So these are now between 0 and 1. We saw that in the first chapter. And I'm going to get the Farid filters, and I'm going to add the edges to our already open viewer. Okay, so it's a little bit hard to see here because in 3D you're seeing sort of the sum of the edges overall, but if you go back to the 2D version, you can see, and I'm going to hide the nuclei, you can see that the edges are highest around the edge of the nuclei. There's still some texture inside the nuclei, but we'll ignore that. Does that make sense to everyone, what we just did? Yep. Okay, so finding the edges is sort of the first step in segmenting. Another step that we want to do is we want to find out what's foreground and what's background. So for that, we're going to use thresholding, which is just finding the, from an image that has continuous values, finding either foreground or background based on some cutoff value. So I'll do some denoising like we did before. Is this imported anywhere? No, it's not. Sorry, guys. My settings are just terrible today. From SciPy, import the image as NDI. It's just a test to make sure you're paying attention. All right. So we do a median filter, which again we saw, and we want to use it because it's edge preserving. And then we're going to use one of the threshold functions built into scikit-image. I think I also need to import this. Okay, so this threshold D will return one value, and then we just want to compare our denoised image to that one value. If you want to look at other methods, you can use, let's do this, from scikit-image import filters, filters.threshold underscore, and then tab. Oh, hang on, I need to control. I need to import it first and then do that. Yeah, so then you can see all of the different thresholding methods, and you could just pick a random one and do a question mark and see what that method is all about. So typically, depending on what your data looks like, you might want to do one or another. And in this case, we've just chosen thresholdly more or less arbitrarily. So now I'm going to add the thresholded image to the viewer. Again, it's sort of handy to get rid of all of them. So this is now our thresholded nuclei. And you can see that there's sort of holes and stuff due to the variations in intensity inside of the nuclei. So we're going to get rid of them. And to do that, we didn't have time to cover morphology, but that morphology means the study of shapes. And it's a common thing in image analysis. So in this case, we want to find all of the holes inside of these objects, and that is in scikit-image morphology, remove small holes or remove small objects, which does the converse thing. So like for example, here in the corner, we see the remnants of a nucleus, and you can see that it's just small isolated objects. So we probably don't want to deal with that. And there's also in between the nuclei, you can see some objects here. So we're going to remove the holes and remove the objects, and then we'll end up with a much cleaner image to work with. So import morphology, remove holes that are more than 20 cubed pixels, remove objects that are less than 20 cubed pixels, and then we've added that to the viewer is cleaned, and you can see that it's much nicer than before. Yeah, some of those are actually connected in 3D, so they don't get cleaned up. You can also look at it in 3D and see what's going on. So we can compare them. Yeah. So that's before cleaning, and that's after cleaning. All right, any questions? No? Okay. Okay, so now we're ready to find all of the connected components of this image. So these are, every nucleus is sort of sitting on its own. We're just going to use this function called label, which grabs all of the pixels that are together and gives it a different label. And then we just add that to the viewer. And you can see that we've done mostly a good job, except that some of the nuclei are touching, and they end up with the same label. By the way, another thing that you can do in napari, which is nice, is you can see the coordinates of the cursor on the bottom left of the viewer. Sorry that the font is not going to be good from the back, and then you can see what the label is that's sitting under the viewer. Okay, so this is now nucleus 14, this is nucleus 9. All of these are labeled as 7. So this is where we want to use watershed. Now the way that watershed works is that it puts certain seeds in the image, and then from there it starts to, it's called watershed because it sort of starts to flood with water. And each of those floods has a different value, and then when they meet, you just have one value on one side and one value on the other side. And it does this by using the image intensity as a bit of a landscape into which to flood. So it will, wherever you find edges in your edges image, the watershed will tend to stop at those edges as if there were mountains in the landscape. And this translates to 3D quite well, actually. So that's what we're going to do. We're going to try to place some markers at the center of each of these nuclei, and then we're going to run a watershed from those markers. Okay, how do we find the markers? Step back. So a very common thing, which is what we did with the two circular blobs, is to have a binary image, and then do a distance transform, which tells you the distance from the edge of the binary image, and that should give you a single point in the middle. But we're going to see that that worked really well for the two perfect circles that we had made before. It doesn't work so well when the edge is a little bit rough here. So if I do this and show them in napari, and I need to change something here, which is loosen their depth. Sorry, I thought I'd changed that. So the points are inside of these shells that we do in, that we're showing the labels as. So they're just normally hidden in the inside. You have to say ignore depth in that labels image so that you can see the points inside. You can see that there are a ton of points per nucleus, and then if we do a watershed from those points, you're just gonna end up with like tons of different labels for each nucleus, and that's not what we want in our segmentation. So we come to our next exercise. So I want you to try any of these approaches, whatever you are thinking about, to see if you can automatically find something that is closer to 1 point per nucleus. And we'll spend a few minutes with that. And then I will crowdsource the solution. And then we'll see what else we can do about it. But I think part of the point of this exercise was to show that it can be really quite fiddly to find, there's a lot of, it's a big parameter space to find, the right way to come to your analysis. And sometimes you get there, but not quite there. Like there's not a point here. I don't know if you want a point of the ones that are only on the edge, but maybe. So with napari, what you can do is get your automated solution and then tweak it a little bit. We saw that a little bit with the painting of the watershed in the other example. Here we can also add points to the points layer that we have. So if I go to 2D, I've got my points layer selected. I can click on add a point. I'm just going to go find this plane where most of the points are, and I'm going to add a point here. Okay, so we just have like an extra point that we can use for a watershed. I might just add one on these two, which also didn't have points. Check my work in 3D. Yep. And I can I'm actually going to get rid of all this because we don't, so there's two options. You can copy what Sean did and then tweak it a little bit, or you can just add a new points layer and then add all of the points yourself manually. So the key is, yeah, do a bit of manual annotation and then go on with our analysis. So does everyone get what I just did? And do you want me to slow down so you can try it, or do you want me to keep going? I'm going to keep going. Okay, so now we have all of these points that we like. To get it back, so remember when I added the layer using viewer.addPoints, I get a layer object. Another alternative is you can grab the layers by name. So if I can also do points equal viewer.layers Sean points, and then that'll get me the layer. And then I can get the array, so I can do points data is equal to pts layer.data. And I can do points data. And these are all the points which included, you can see all the ones that the algorithm found, and then these are the ones that we added later on. Okay. All right, so now we have our seeds, and we can do a watershed coming off those seeds. The only small caveat is that watershed doesn't take in coordinates. It takes in an image of the same size as your result image with different labels, so different integer labels at each of those positions. So we can do that here, here. So grab the marker locations. Because this is such a common thing that you have coordinates and you want an image like output, there's a utility function in scikit-image called label points. You give it the coordinates and you give it the shape of the image that you want, and it'll just put a different label at each of those coordinates. And the last thing that's important to know about watershed is that just picture, a landscape. If your point happens to be on like a little lake in a mountain, it's never going to get around the boundaries of that lake, and it's not going to fill in sort of the broader landscape that you're interested in. So in order to avoid some of those issues, I'm running a dilation, which makes the markers sort of a bit bigger, and they might be bigger than whatever local environment they're embedded in. And then I do the watershed, giving the edges image, the markers that I've just defined, and a mask so that it doesn't flood into the background. Okay, so now I'm going to do that. And that is our final segmentation. You can see that the nuclei that were together before are now separated. This should be two things, but it is one thing, so I suspect that it just never got, despite my dilation, one of those seeds never got outside of its own little lake. We can go back to 2D to have a look here. You can see it. See how one of the labels is sort of stuck into its little environment. So again, this is something that you could do with painting. Actually, I might show off a little napari goodness here. Okay, so say you have this situation where you have these two, so it's a little unclear whether this is one object or two. It's actually a cell that is dividing, so all of the chromosomes have gathered together, and there's going to be a split in the middle. So what we want to do is separate those two layers manually, and you can, in 3D, apply the eraser. And I'm gonna make it a bit smaller so I don't obliterate the whole thing. And now I'm like milling. This is very Minecrafty. So I'm just like milling into it. So you can see now the objects are separate. And now I'm going to go back to 2D so I can grab that label. I'm going to do a color picker. So I pick that label. And then I'm going to add the fill. Now, by default in 2D, I'm only editing 2 dimensions. So I can say now fill in all 3 dimensions of the data. Okay, and now I have that. Okay, so now if I go back to 3D, I have my, oh no, I filled that one. Please tell me undo's not broken. Undo's not broken. Okay, undo is like, for some reason, it just breaks all the time. Yeah. All right, so there you go. You have your separated nuclei in 3D. I could go and fix that, but I'm not gonna. All right. Any questions about that thing? Nope. Good. Okay. So this is sort of the big thing. So as I said, like everything that we just did, you can, for many kinds of images, you can probably find a pre-trained network that gets close to what you want. But eventually, this is what you get. You get like an image with integer labels for each of your objects. And typically, if you're doing science, what you want is to actually like find out things about those objects. So that's what we're going to do here. We're going to use region props. I'm getting rid of anything that touches an edge because I don't, you don't want to count a nucleus that's cut in half as being a nucleus that's half size. So I'm doing clear border here. And I can show what that looks like, but I haven't, so I'll just do it here. Add labels. Interior labels. It's important that we keep the scale the same for all of them, so adding that. Blending equals translucent, no depth, so I can see the point still. And name, I'm going to say. Okay. So if I get rid of segmented, you can see that these are now the objects that we're taking measurements from. Okay. Now with region props, just for historical reasons, some properties are defined for 3D or n-dimensional objects. Some properties are only for 2D. Here, I'm just going to run through all of the properties supported by region props. And then this will, if I try to access a property that's not implemented, it will raise a not implemented error. So this will just tell me which ones are available for 3D and which ones are 2D only. And you can run this cell, and hopefully the lower list will get smaller and smaller every year that you run this. So like orientation, I don't know why that's not 3D. We can figure that out in the sprints. You do? Oh, you're the n-dimensional. Oh my God. Okay. A while ago. All right. Yeah, that's sort of the classical API for region props is you pass in region props and you get a list of custom objects, and each object has all of the properties on it. If you want to do data science, you probably want to get a pandas data frame with all of your measurements. So to do that, you use region props table, which returns a dictionary mapping column names to column values. So that's what I'm going to do here, and I'm going to measure the label value, the slice, which are the coordinates of it, the area, the mean intensity, and the solidity, which is how close to a perfect sphere a thing is. And then you get a nice little data frame. And you can use Seaborn or your favorite data science library to do some data analysis on this. And you will see that the two nuclei that are undergoing cell division are sort of separated from the other nuclei. Okay, so almost at time. Let's do these two exercises. So one of the things is that area in 3D and in 2D. This is something that we're also trying to fix in scikit-image. It always means number of pixels, actually. So if you want to measure it in microns, you know the scale, you know the size of a pixel in your data set. So the question is, what is the area in cubic micrometers? And can you add that to your data frame? And then the second thing is, what if you want to look at the nuclei colored by some property, just as a way of doing data visualization? So there's a function that can help you do that. So yellow stickers, and yeah, we'll come around. Okay, so I want to have a little bit of time at the end for general questions and stuff. So I am going to go through the solution now, and then yeah, we'll just be around to help if you have further questions after. This is more of a pandas than a image analysis question, but I guess the point is to show you like the kinds of things that you do in image analysis. So we have our table, which we call info table, and it contains a column of heading area, and we know that that's in pixels. So if we want to get it in micrometers, we do, by the way, fun fact, you can actually do, this is a valid Python name per pixel. It's equal to NumPy.product of spacing. I think that's the thing, yep. And now I'm just going to say info table of area cubed is equal to info table of area times micrometer. Oh, the autocomplete doesn't work with it. That's interesting. Okay, and now I can do info table.head, and you see that now I have another column that shows the physical measurement of our pixels. Okay, does anyone have questions about that? No, good. And the last thing, let's look at a measurement that has some variables, so solidity, for example. Actually, I feel like the area's got a bit more variance. So, all right, so now I can do, I basically want an image such that the color of a pixel is the value of that object in the region props. And to do that, I can use from scikit-image util import map array. Then I typically look at the docs of whatever I've just imported. Okay, so this is the input array, so this will be our segmentation. The input values is the segmentation label, and the output values is the the value of the feature that we're trying to color by. So to do that, I think I actually got rid of my label because I put it in the index, but I think that's okay. All right, so I want to do feature image is equal to map array. Is it called segmented? I'm going to do the cleared interior labels. Okay. The input values is np.asArray of info table.index. my pandas is like not super amazing, so everyone cross your fingers, please. I'm actually going to the pandas tutorial tomorrow. All right, so an np.asArray of info table of area. Didn't crash, that's good. Add image of feature image scale equals spacing. Nope, not equipped. I think that worked. Let's have a look. We probably want a cooler color map on this, but yeah, you can see the area of these is smaller, so it's less bright. And I can just make it fancier by choosing that. So that's our feature values displayed on our image. And that is basically it. There's some advanced notebooks that I suspected we wouldn't get to, but feel free to do them at your own time. And we have actually a couple of chat rooms that you can go to. So scikit-image.zulachat.com and napari.zulachat.com. It's basically like Slack, but better. I need to turn on the public view for scikit-image. Yeah, and feel free to reach out for us there. And in the meantime, we've got 5 minutes. I'm happy to answer questions, help you with, if you have your own data questions, happy to help with that as well. That's it. Yes? The final one? Oh, okay, yeah, sorry. The index is my own fault. So if I do feature, info table dot head, you can see that the label is the value of the segment. And the label is not a normal column, it is an index of the pandas. And I did that manually over here. I'm just going to close this. Dot set index label. I probably could have, should have done set index label. Oh, I put tab and it's unhappy. Oh. Let me look at some docs. So table dot set index question mark. Dropped. Okay, so when you set an index, you can remove the column itself from the columns. And it's probably better not to, so I'm going to say drop equals false. And now if I do info table.head, you can see that I have the index, but I also have the column. And then down here, I could do label, and that is much clearer, isn't it? Yeah, so good question. There is like a subset of pandas users that think that the index was not a good idea. But so I guess they have a point. Any other questions? Cool. Well, thanks for coming. Hopefully you learned something. More questions?
One last story.
Yeah, go for it.
So could you go, when you showed this interactive demo, erasing the boundary between the two cells,
Yeah.
so I tried to replicate it, and at the end, my labels are smaller because I erased. But I think you fill at the end.
No, I didn't fill it.
So
I was just a little bit, yeah.
okay.
You could refill it, right? You could take now the two labels and reapply. You could take your new image and go back to the original thresholded image and do watershed again. Your seeds are now your full segments, and they will just fill into each other. So that's how you would do that. Yeah. Yeah, you can see there's still a gap here. Cool. Well, thank you, everyone, and see you. see you around. I will also say, if it's your first SciPy, you should stay for the sprint. That kind of, it's really, really nice experience.